Hi, so my name's Varun, and welcome to Mathematics of Animation. So I really like CodePen. It's an amazing community. I use the tool all the time to build stuff for myself, making little experiments. But I probably spend a lot more time just looking at all the amazing work there. And there's some truly fascinating animation and interactive and just in general front-end engineering work that's showcased there. And one thing that quite often happens is I look at this work and wonder, how did they do that? Because I would really like to know, how did they do that so that I can do that for myself? And the benefit of it being CodePen is you can actually go in and see the code yourself. So I spend a lot of time looking at some of my favorite pieces up there and reading the code, reading tutorials and blog posts. And one thing that I discovered was a lot of it came down to just understanding a little bit of basic math. And just that little basic information goes a really long way that allows you to build some truly amazing work. And this was especially important for me since I tend to do a lot more reactive animations, which are slightly different to the general timeline-based animations. So in a timeline-based animation, you have a timeline, you set your keyframes, and things sort of tween between those keyframes. In reactive animations, instead of having a timeline, you're usually driving that animation through some sort of events, whether that's user interactions, so for example, the mouse cursor moving around a page, or gestures. So the middle example there is Google Chrome on iOS, where when you pull down and you move your thumb around on the page, that's what drives the animation for that header. But also those events could come from some other source. So for example, a backend service. So Uber, for their map, they tend to animate the map based on data coming from their backend API. And that's what's driving the animation in that scenario. So when you're working with these events, it's kind of important to understand what that math is that's driving these animations so that you can actually map those events to these things that are moving onto the screen. So with that in mind, I just wanted to share a few techniques that I tend to use a lot in my work, and then talk about the mathematical concepts behind them so that you can leverage them and build things for yourself. So I'm going to start with coordinate geometry. And when designers and illustrators, when they're creating their work, they tend to think in shapes or images. But when we want to translate that into something we can render onto the screen in a web page or in an application, we need to convert those shapes and images into numbers and code. And one way to do that is through coordinate geometry, and more specifically, the Cartesian coordinate system. This is something you probably have come across if you've worked with CSS or HTML or Canvas or WebGL, or even worked with tools such as Illustrator or Sketch. And in Cartesian coordinates, the idea is that you locate points on a 2D canvas by finding how far away they are from the origin. So for example, up here, the point xy is x units away from the origin in the x direction, and y units away from the origin in the y direction. And this is pretty handy. Once we can locate these points, we can get a whole bunch of those points, join them up together, and create shapes on our canvas, right? And this is pretty handy. This is the concept that you use in all kinds of graphics programming, whether that's for the web or for using OpenGL or whatever, right? But what if you wanted to create something a little bit more specific like this illustration? In this case, the shapes that you're building have a very specific, has a very specific shape to it. Even if you reduce it down to something like a hexagon. If you wanted to draw this, you need to figure out the location for every single point of this hexagon. So what's the coordinate for that first vertex? Then find the coordinate for the second one, the third one, and so on. And then imagine if you were animating this every time you move this hexagon. For every keyframe that you're creating, you need to go and calculate those vertices every single time. Now, I don't know about you, but that sounds like a lot of work to me, and I tend to be fairly lazy. So is there a better way to do this, or a slightly simpler way to do this? And the answer is yes. There is another coordinate system out there called the polar coordinate system, which we can leverage to build shapes such as this. And polar coordinates are fairly related to Cartesian coordinates, but the only difference is instead of thinking about points in x and y, we start thinking about them in terms of r and theta, where r is the distance between the origin and the point that you're trying to locate, and theta is the angle of the direction of that point. So when you draw a line from that point xy to the origin, that line has an angle from the x-axis. That's what theta is. So if you know those two things, you can now start to locate any point in this 2D space. And the nice thing is we can switch back and forth between the two. So if we wanted to convert something that's based in polar coordinates into Cartesian coordinates, well, x is simply r times cosine of theta, and y is simply r times sine of theta. So we can switch back and forth between them, and that comes in pretty handy. Sometimes it makes sense to think in polar coordinates, but then other times you might want to switch it into back into Cartesian coordinates when you're actually drawing the shape. So in this scenario, theta allows us to control the sort of the direction in which where we want to place the point, and the radius allows us to control how far away we want that point to be from the origin of our 2D canvas. So why am I telling you about this? Well, when we're dealing with regular polygons, these come in really handy. Regular polygons are polygons that are sort of symmetrical, where each side is the same length, and they have this special property. And that property is that, first of all, you can locate all of the vertices of that polygon on a circle. Next, if you were to slice up that polygon into triangles, so just simply connect all the opposing points through diagonals, it splits the polygon into little triangles. And each one of those triangles has the same angle at the center of this polygon. And that's really important. We can calculate that angle by the formula up there, so 360 degree divided by the number of sides. So if I were to draw an octagon here with 8 sides, that angle comes out to be 360 divided by 8, which is 45 degrees. So following that, we can locate the theta value for every single vertex, where the first one is at 0 degrees, second one at 45 degrees, third one at 90 degrees, and so on. And that's pretty awesome, because if we were using polar coordinates, we have the theta value already, and all we need is r to actually render out this shape. So in order to render that shape, we go back to our polar coordinate system, and we start calculating the x and y values using the formula I shared earlier. So x is r times cos of theta, and y is r times sine of theta. So we start with theta as 0 for the first point, 45 for the second, 90, then 135, 180, and so on. And that way we can locate the vertices of all these points and actually create the shape that we're trying to build. So next up, let's talk a little bit about something called parameterization, and that's sort of related to this idea of geometry that we're creating. Parameterization is this concept where you take a geometry that you're trying to create and try to reduce it into some kind of variables that would allow you to build out that geometry. And parameterization itself is a generic concept in computer science, but for now, I'm just focusing it on its application for creating graphics. So in our case, we're building out shapes. So if you think about the variables that we need to build a shape, well, we need all the locations of all the vertices in order to build out that shape. That's one way to parameterize that shape. Another way to parameterize that shape is, if you think about it, if you have the number of sides, we can figure out what the angles are for each one of those vertices. So the only other thing that we need to build out that shape is just the radius. So we've reduced those 6 vertices down to just 2 variables. All we need is the number of sides and the radius in order to build out this shape. So that allows us to do something like this, where we have our little demo that's rendering the shape, and I can connect it to a slider that changes the number of sides, and that's what drives the shape that we're rendering out. And then the radius simply controls how big or small that shape is. So now we're starting to get somewhere, right? So we're starting to create geometry dynamically. So how would you go about doing something like this? Well, for that, I'm going to walk through a little bit of code for a polygon generator. And the idea is this function will take 2 variables, a side count and radius, so the number of sides for the polygon that you're generating and the size of that polygon. And using that, it's going to generate all the vertices needed to render out that shape. So the first thing that happens inside this function is it calculates the angle. So 360 divided by the number of sides. Then we create a placeholder list for all the vertices that we need to generate for this shape. And to do that, I have a little one-line JavaScript function here that accepts a count value. And what it does is it generates a list. So if you give it a count of 5, it will generate a list of 0, 1, 2, 3, 4, 5, and return that to you. And then next step, what we do is we iterate over this list, the placeholder list that we generated, and then we go through and generate each vertex one by one. And to generate that vertex, we need to calculate two things. We need to calculate theta and r. Well, r is simply the radius that we passed into this function. Theta, on the other hand, is angle times the index of the vertex that we're trying to calculate. So if you think about, go back to that circle image that I showed. First point sits at 0 degree, second one at 45, then 90. So essentially, it's just multiples of that angle that we calculated, right? 45 degrees. And that's what's happening here. The only thing to keep in mind here is when you're working with graphics, regardless of what kind of technology you're working with, you generally need to specify angles in radians instead of degrees. And I personally find easier to reason about angles in degrees, but then have to convert it into radians in order to use it, to pass it on to whatever is rendering things. And to do that, again, I have a little one-line function here that converts the angle from degrees to radians. And to do that, all it does is multiplies the angle by pi and divides it by 180. So using this function, we're able to generate all sorts of polygons that are regular polygons based on the side count and the radius that we pass in. So let's see another application of this. So this is an animation that was originally created by Chris Gannon. He does some truly fantastic work. And in his animation, he built it out like something like this to begin with, where it was a hexagon that had this really beautiful light diffusion animation happening to it. So what I did here was take his original animation, and which had the hard-coded hexagon path placed inside it, and replaced it with the polygon generator. So now, instead of that shape being hard-coded, that shape could now be driven dynamically through events. So in this case, I linked up that polygon generator to the sliders again. So the number of sides allows us to change the shape of the object that's being animated, and the radius, again, allows us to control how big or small that object is. So that's pretty cool, right? We're building out an animation, we're building out geometry dynamically, and then we're attaching it to animation, which can be morphed in real time too. So let's go back to the GEMS illustration that I showed you. How do we apply parameterization to it? So if you look closely, this one's a little bit trickier, right? It's not just that one shape that you're building out. Each of these objects has that one outer shape, but then that same shape repeats on the inside, which is slightly smaller. And then there are faces that connect each one of those inside and outer shapes. So how do you go about doing something like this? Well, once again, we can leverage that idea of parameterization, and we don't need to provide any more variables because if you look closely, the outer shape can be driven by r and theta still. The inner shape is slightly smaller, so we can choose to make that ratio dynamic, and that would be the extra variable. But you can also hard-code that. So in my case, I hard-coded that to be just simply half of the radius that you're passing in. So we can calculate that inner shape using r over 2 instead of the full r. And we calculate the points the same way as before. So x is r cos theta, y is r sine theta. And for the inner shape, x is r over 2 cos theta, and y is r over 2 sine theta. But then what about the faces? How do we build these faces that connect the inside and the outside? Well, if you think about it, the faces are simply made up of vertices of the inside and the outside. So all we need to do is go and find the coordinates for the sort of the similar sides for both those shapes. So we pick the first side for the outer shape, the first side for the inner shape, take the 4 points and connect them together to form the face. So I used exactly this concept to convert that original illustration into something a little bit more dynamic and reactive. So this is built with SVG and React. And the idea here is that I constructed the geometry dynamically using that polygon generator again, and then wired up the mouse pointer to calculate the direction of the light. So dynamically now, as the user moves the mouse pointer on the screen, those gems are lit up differently in different contexts. So definitely it's not as elaborate lighting as the original illustration, but it's starting to get there where you can do sort of interesting stuff where now you can imagine that some kind of interaction from the user is driving these animations live instead of it being pre-rendered and static at all times. And of course, we can use that same idea of parameterization to build out patterns instead. So previously, when we were using polar coordinates, we were using it to locate the vertices of a geometry and then connect them together to form a shape. But we can use exactly that same idea to construct patterns. So in this case, you'll notice that instead of connecting these points together to make a shape, we're actually connecting these points together and we're simply placing dots at every single one of those locations. So how do we do this? Well, similar to before, we start by creating, we can sort of split that pattern up into multiple circles. And each circle is one layer of that animation. And now that angle between the different dots, it's similar to the regular polygons before. To calculate that angle, we simply decide how many dots that we want to place on that circle. 360 divided by those number of dots will give us the angle. And then we use that angle to locate every single dot that we're placing onto this page. The only difference now is instead of just being one circle, we have many different layers. And each layer has a different radius. So for the innermost circle, we use R1 to calculate the X and Y values. For the next one, we'd use R2, and so on. And that allows us to construct really elaborate patterns like this. And then we simply animate them to actually do something like this. So speaking of that animation, let's talk a little bit about waves and oscillations. Starting with the simple sine wave. You've probably seen this many, many times, and most people see it and ignore it and move on to something more flashy and more cool. But the nice thing is the sine wave is actually extremely powerful. It allows us to do some really, really interesting work. And a sine wave has this quality where if you iterate the angle from 0 to 360 degrees, it forms that wave-like pattern, right, where it goes from 0 to 1, down to -1, and then back to 0. But the interesting thing is, you don't need to stop that angle at 360 degrees. You can keep going, and that pattern will keep on repeating. So you get this amazing oscillation behavior without having to worry about, do I need to reset this angle now, or do I need to go to a specific angle? You can just keep looping over it and keep adding values to it, and you get the same motion every time. And the cosine wave is basically the same thing as sine wave, but there's a slight offset to it. So technically, you can use them interchangeably when you're generating wave-like motion. So for now, I'm just going to be focusing on the sine wave itself. So we can use this sine wave to create amazing animations like this. So this is an animation by Dave Whyte where he's using the sine wave to drive the hexagon pattern up and down and basically morphing that entire geometry. And you've probably heard of Dave Whyte. He also goes by the name Bees and Bonds. And a lot of his work tends to use sine waves. So here you'll notice that there's quite a few examples. Up top, he's using the sine wave to control the size of blocks, so they increase and decrease in height. He's using the sine wave to control the radius of those dots in the hexagon to create that nice wave-like pattern, to move those blocks around in X or Y direction, or to move the points around radially, or even to just completely morph the shape of an object. So it's a really powerful concept. Just by using that one simple, humble sine wave, you can do some amazing work. So how do you go about leveraging this? Well, let's start by looking at how you would use the sine wave in general in an animation loop. So we start by declaring the initial value of theta that's going to be driving the entire sine wave. So 0 sounds like a good place to start. And then we create our animation loop. So in this animation loop, we're simply going to be iterating theta. So we don't need to worry about stopping at a particular point or resetting because sine is a repeating pattern. So we simply add a line of code there that says theta equals theta plus some static value. And that static value really defines how fast or slow you want your animation to move. And all of these values are in radians, so I picked 0.15. That seems like a decent speed for now. But if you're changing that rate, you can change it to make your animation faster or slower, or even change it over time to give like an easing effect. And then we simply calculate the current value of that sine wave on every single animation loop. So we calculate x as sine of theta, and then on every draw loop, we use that value to run some kind of animation. So for the first example, we can use that sine animation to drive translation or motion in one or two directions. So in this case, we're oscillating that red ball across the screen. And the way we do that is we have that ball has a starting point, and all we want to do is animate it around that starting point, so it's oscillating with an amplitude. So in our animation loop, we calculate the current x position as the starting point, so x start, plus the amplitude we want it to oscillate by. So in my case, I picked 300 as a value, times the sine wave that you're generating. And that's going to move the x position of this ball from, at the leftmost would be x minus 300, at the rightmost would be x plus 300, and that's what produces this horizontal oscillation motion. We can apply that exact same idea for scaling. So in this case, our amplitude of scaling is, I picked as 1, and then we multiply that by the sine wave that we're generating, and then we add it to the starting point of the scale. So in this case, the starting scale is 1, and then we're also oscillating by 1. So you'll notice that it goes all the way down to 0, then comes back fully to its normal size, and then goes back down to 0. And of course, by changing that amplitude, in this case that I have 1, you can change that animation over time dynamically, responding to different events or just responding to user interaction. And finally, we can also use this to drive rotation. So in this case, we're trying to rotate the red ball around the black dot that's in the center of the screen there. So to do that, now we need to calculate both x and y values for that ball. So x in this case is the x coordinate of the origin. That's the black ball in the middle, plus the distance, and that's the distance between the black dot in the middle and the red ball that's rotating, times cos of theta. And this is the only time where sine and cos will matter, because we're dealing with polar coordinates again. So the x value always has to be in terms of cos, whereas the y value has to be in terms of sine. And then that allows us to calculate the x and y coordinates to create animations like this. So let's see some real-world examples of this. So this is a piece that I found on CodePen. It's a little rocket that's rotating around the moon. So in this scenario, the origin is the center of the moon. The distance is the distance between the center of the moon and the center of the rocket. And then we're simply iterating theta over time to generate this rotational motion around the moon. So pretty cool stuff. We can also use it to do something a little bit more complex. So going back to some of Dave Whyte's work, this animation is called Swimmer. And you'll notice that it's constructed out of a lot of different points again. So in this scenario, we're using parameterization, but instead of placing it using polar coordinates, going back to the Cartesian coordinate system to generate that diamond pattern, and then animating each one of those points that you see in that pattern. And if you'll notice closely, the center row vertically, all the dots in the center row simply move up and down vertically, and that's the only animation. The row next to it on the right-hand side, the dots are oscillating up and down, but there's also a slight horizontal oscillation to them. And as you move further away from that center, that oscillation increases more and more. So all of these dots are oscillating, but not at the same rate. There's a slight difference to every one of them. So that's the last part of it. So you're using sine waves to create these animations, but instead of moving everything at the same rate or at the same time, just by offsetting them, you can create really beautiful patterns. And the way you do that is something like this, so we start off with a ball that's oscillating up and down on the canvas. So in this case, we started off with theta as 0, and then we increment theta by 0.1 on every single animation loop. Then we add a second ball. But in this case, instead of starting at theta as 0, we started at 0.4. And then we add a third one that started at 0.8, and a fourth one, and a full row of them, and then the second row, and another layer. And each time, we simply offset the starting point that allows us to create this really beautiful wave-like pattern. And by layering a lot of them, we get this really interesting motion where they go out of sync and they keep moving around, and then at some point they come together and they synchronize for just a moment, and then they go apart again. So that's one way to generate those offset patterns. The other way to generate those offset patterns is to use different amplitudes. So instead of oscillating all of them at the same amplitude, so oscillating them all at 300 pixels or something, you can choose a different value for each one of them, and that will give a different kind of effect. And that's what's happening here. So instead of oscillating each dot at the same time, the horizontal motion, there's a different amplitude for depending on which row that dot belongs in. Well, let's go back to that rocket example once more. So in this example, you'll notice that the rocket is moving on its own, but it's also reactive. I can actually drag the rocket with my mouse cursor, rotate it manually, or even just like toss it, and there's a little bit of momentum to it. So how do you do that? How does it know that when your mouse cursor is moving around the page, where that rocket needs to be? What angle is it going to be at in that rotation? So in order to do that, we need to talk about yet another mathematical concept, and this one's known as solving triangles. So solving triangles is this idea where you have a triangle and you know something about it. You know one angle, maybe you know a couple of angles, or you know one side or a couple of sides, or a mixture of like one angle and one side, and you're trying to find all the other missing sides or the missing angles. So for now, I'm going to focus on a simplified case of this, which I tend to encounter a lot while making animations, and that's the right angle triangle. So since it's a right angle triangle, it has a few properties. One angle we know is 90 degrees. And then there are a couple of other angles, which we know have to be less than 90 degrees, and they should add up to 90 degrees. And then it has three sides, the opposite, the adjacent, which is the base of the triangle, and then the hypotenuse. So once we know this, we can start talking about how would we go about solving this triangle. So we often find ourselves in these scenarios where, okay, I know this is a right angle triangle. I maybe know two of the sides, and I need to figure out what the angle is between the hypotenuse and the base, or one of the other angles. Or I might know that angle in one of the sides, and I need to figure out the third side. So how do we do that? Well, for that, we need to go back to high school for a bit. You might remember this mnemonic device of SOHCAHTOA. Well, that's exactly what we're going to use here to figure out those angles or the missing information. So we have these three formulas, which you tend to use quite a lot to solve triangles. So sine of theta is O over H, cos of theta is A over H, and tan of theta is O over A. So if I wanted to figure out what that angle theta is, I can use that last formula of tan of theta is O over A and calculate theta as arctangent of O over A. So arctangent is simply an inverse of tan. So if you move tan from the left-hand side of the equation to the right-hand side, it turns into arctangent. So let's see this in action. This is a demo from the P5JS examples. And it's a little example of eye tracking, or sort of a simplified version of eye tracking. So you'll notice that these three eyes sort of track the mouse cursor, which is the purple dot, and they try to always look at that mouse cursor. If you look a little bit closer, you'll notice that the pupil of the eye, the black part, is simply rotating about the center of the eye. So it's a very similar setup to that rocket example, except instead of rotating outside the moon, it's rotating inside the eye. So as I move the cursor around the page, what I need to do is figure out the angle of rotation for that particular circle. And the way I do that is by solving triangles. So you might be asking, wait, what triangle? What are we solving here? So let me enable some debugging here. So you'll notice that if we connect the purple dot, which is the mouse cursor, and the blue dot, which is the center of the eye, it actually forms a right-angled triangle. And since we know the location of the center of the eye and we know the location of the mouse cursor, we actually know the base of the triangle and we know the height of the triangle. So we can use those two values and put it into our arctangent formula and calculate that angle that the eye needs to be. So in this demo, what's happening is we're solving three triangles at the same time, one for each eye. And as the mouse cursor moves around the page, it's simply figuring out the angle and rotating the black circle by that value. And this is sort of a more elaborate version of that eye tracking. This one was built by Hakeem El-Hattab for the Net 404, just their 404 error page. And along with that eye tracking idea, it has a few more things happening here. So the eyes are blinking, and you can add more layers of animation to that initial reactivity that you're creating. Let's look at another example of solving triangles. So in this case, this is a little animation I made a few years ago where I'm trying to replicate a very cartoony lighting system where you can see the yellow circle acts as the source of light. And based on how close or far away I am from the triangle, that controls this glossy shine that you can see on the page there. So again, how am I solving triangles here? Let's go to the debug version of this. So in this case, you'll notice that we know the location of the center of the triangle. We know the location of the source of light. And what we really need to figure out is the 2 points that make up that gloss. And there's one other variable that we actually know in this case. We know the spread of the light. And spread of light in this case is a triangle that we're using here. And in this case, that spread of light is controlled by the distance between the source of the light and the center of the triangle. So the further away I am from the triangle, the wider that triangle gets. And the closer I go to it, the narrower that triangle gets. So in this case, I actually know the angle of that triangle at all times. And then finally, we also know the distance from the center of the triangle to where that gloss is being drawn. That's the thick green line that you see there. So since we know that one distance, we know the angle, we can actually calculate the location where those vertices are going to be placed. And that allows us to figure out how long that gloss needs to be and render it out as a stroke. One more example of solving triangles. So this one is from the Paper.js documentation site. They have an example of metaballs. Normally, metaballs are built using shaders, and this is a slightly different version of metaballs where instead of using shaders, it's built using canvas and just connecting shapes together. So in this case, what you'll notice is the metaballs are made up of two circles, the little circle and then the big circle that I can move around with my mouse cursor. And then if the two circles come close enough, there's a connector that becomes between the two of them. And that's where we're using the idea of solving triangles. So for this particular one, I have debugging enabled. So you'll notice that as I move the circle close enough, the connector shows up. And then the connector is connecting 2 points on each of the circles. And those 2 points have handles that decide how narrow or wide that connector needs to be. So in this scenario, what we need to do is figure out that angle of that connector, that handle. And the way we can do that is we know the radius of the circles, we know the point at which that handle is going to be generated. So again, it forms a triangle, and we can use that to calculate the angle of that handle and then generate this connector. So as I go closer or further away, you can see the connector moving wide or coming closer. And of course, this concept is used a lot in sort of physics applications, so for game development. So here I have a link to a blog post by Rachel Smith, which covers the idea of solving triangles to actually build out levers. So sort of similar idea to what certain games like Angry Birds or any of those kinds of games tend to use. So if you're kind of interested in this idea, I would highly recommend reading that blog post to get a lot more detail about how to solve triangles. And I'll share a link to that in my slides after the talk. And finally, I wanted to talk a little bit about easings. So if you've ever done CSS animations, you're probably dealt with some kind of easings, right? When we create our animation, we specify what kind of easing we want, whether it's linear or a sine wave or cubic or quadratic, all kinds of stuff, right? So CSS has a lot of easings predefined, and we can simply select which one we want to apply. And each one of those easings that we choose is known as an easing function. So an easing function is something that drives the relationship between time and the progress of that animation. And a lot of those functions are predefined, except the cubic Bezier one. That's something that we can actually configure to our liking, even in CSS. So a cubic Bezier easing is essentially a curve of this sort. And usually you need four variables to generate that curve. One, the start value, the end value, and then the location of the two handles. However, in CSS, that start value is always set to be 0, 0. The end value is always set to be 1, 1. So the only thing we need to provide to generate this curve is the location of the two handles. And that's what those four numbers are. So if you've ever written a CSS animation with cubic Bezier followed by four numbers, those are the locations of those two handles. So the first one is the x-coordinate of the first handle. The second one is the y-coordinate of the first handle. And then the last two are the x and the y-coordinate of the second handle. So we can use this to generate more customized curves that define the easing that we want to use. And there's many tools out there. If you just search for cubic Bezier, you'll find hundreds of tools out there that allow you to generate those curves. But when you're working with JavaScript animation libraries, you can go one step further. You can actually build your own easing function. And one of the most popular ways to do this is, on the web especially, is to use something called Penner's equations. And Penner's equations are a certain type of equations that take four variables and then construct how your animation is going to progress. So how is it going to go from the starting point to the end point? And the four variables that you need that equation receives is starting with the current time. So as you're tweening from start to end, what is the current time in your animation loop? And this can be in any unit as you want. It could be in seconds, in milliseconds, in frame counts, as long as you're using the same unit throughout your animation. The second argument that's passed in is the start value. So this is the start value of the property that you're animating. The third is delta, which is the change between the start value and the end value of the property that you're animating. And then finally, the duration, the total duration of the animation or the tween or the transition that you're generating. And then the body of the function usually consists of something like this, where you have the start value plus the delta times some kind of multiplier. And that multiplier usually comes from a transform. So that transform kind of decides how your animation is going to behave, whether it's going to have a linear ease, if it's going to have a bounce ease, or some kind of really crazy ease that you're creating. So let's look at an example of an easing that's generated using the Penner's equations. So this is something I found from Patak, who's a really talented GIF animator. And on his blog, he shared this function that he uses quite often to generate easings. So down here, you'll notice is the actual Penner equation, and that start value plus some kind of multiplier that we're generating, and then multiplied by delta. So that transform function is really the only one we mostly need to care about. So in this case, this is the transform function that's being defined. So there's a lot of math going on here, and it takes a while to get your head around that and understand exactly what's happening here. But the nice thing about this is you don't need to worry about it. You can just go ahead and start using it, because the only thing that you need to care about is that first line of code, the g equals 6. By modifying that value of g, you can generate all kinds of easings. So it's a really nice formula that allows you to generate different kinds of easings just by modifying that one value. Here's another example of bounce easing. So this is something from Matt Delaurier's eases library. So generally, if you go and look at code for a bounce transition, you'll notice that there's a lot of code there. There's like 4 or 5 lines of code that decide what kind of that animation, what that function needs to be to generate that easing. But this is a much more stripped down, simplified version of that. So in this case, the nice thing is you'll notice this number here at 13. That constant is the only thing that drives the springiness of this bounce easing. So by increasing or decreasing that value, you can control whether this is going to be a really stiff spring, so it bounces very slightly and stops right away, or it's going to be a really, really flexible spring where it wobbles around many times before coming to a stop. So again, it's a really, you don't need to understand the full math here, but just by knowing what one number you can change in order to generate different eases allows you to construct really interesting behaviors. And once you understand this idea of what a Penner equation is and what that transform part is, you can start using it to construct your own custom easing functions. So most JavaScript animation libraries will allow you to define that. So you don't need to worry about constructing the full Penner equation. The only part you need to worry about creating is the actual transform itself, so the one that depends on the current time. So this is an example of how you would define a custom easing for Anime.js, which is a fairly popular JavaScript animation library. So you can replace this with the body of this function with any of the previous 2 examples that I showed, and use those custom easing patterns in your own when you're working with Anime.js. And that allows you to make interesting things like this demo that I created, where on every click, all of those little layers of the box animate with a different spring level. So in this case, I'm constructing 5 or 6 different kinds of spring easings, and then layering them on top of each other to create this staggered effect where each box sort of bounces at a different rate. And that's about it. Thank you for coming out.